Hello and welcome to SMARSLab Live. I'm Kevin McAleer and today we'll be looking at servos and the PCA9685 servo board, bit of a mouthful. So these are little things we'll be looking at today. Got an example of a couple of them there. And we'll be using the Arduino IDE and Raspberry Pi 4 to do some coding. And for people who are not aware of what SMARS is, it's an amazing low-cost open source 3D printable robot. It's very easy to print yourself and assemble. Very little programming or electronic skills required. So it's really easy to get into robotics. So what we'll do is we'll head on over to some preamble that I've prepared. So this is just a bit of an introduction. I'll just get out of the way there. So that's a couple of my SMARS robots this afternoon. And the one that's sort of centre shot here, this is one of the quad robots. He uses a number of, I think it's 8 servos to make him walk. So there's a couple of different types of servos. The main 2 different types is the sort of SG versus MG. So I'm not sure what the SG stands for, but it's the MG's metal gear. So the standard ones are plastic gears. The metal versions have obviously got metal gears inside and therefore a lot more robust, a bit heavier, use a bit more power, but they can have a much more resistive force, so they can keep the position, hold the position. The SG90s, these little blue ones at the bottom here, these are the most common servos that you'll come across, and they can. They can't lift an awful lot of weight, but they can certainly lift their own weight. Certainly keep the SMARS quad on his feet. And they can turn between 0 and 180 degrees typically, sometimes a little bit more than that, but that's the official kind of range. You can get continuous rotation servos, but really that's just a geared motor. So I would say proper servo just has this restrictive 0 to 180 range. And you can also see on this diagram here we've got some of the PCA9685 boards as well, so we'll look at them in a minute. So what do I mean by this strength? So you'll see on the servo it'll talk about how many kilograms per centimetre, and if you look at this little servo horn that we've got here, that's what they call the bit that fits on the top of the servo. 1 centimetre away from the centre point, the pivot point, it can hold 20 kilograms of weight. It can continuously hold that. So that's that particular type there. They're quite expensive, them ones, compared to the SG90s. And it can hold that force and keep it there is the idea when they've got this sort of stamp on it to say it's guaranteed. So much less so for the SG90s. So how do they work inside? Well, they've got this little gearbox first of all. So what that does is just steps down the turning force from the motor, and by reducing the gears down, you'll see it goes from small to large, small to large, small to large. It does that several times. That gives it a lot more torque. So it's got a higher torque. It turns a lot slower, but the force at which it can turn is a lot more than if that motor was just directly the horn was directly on top of the motor. And this gearing ratio as well also enables us to sort of control the speed without having to change the motor. So when they manufacture these, they might do 60 RPM, 150 RPM, 300 RPM. And you might have seen some of the other videos that I've shared earlier in the week. They had different speed of motors in the SMARS robots. So these are typically how they're sort of configured. There's a little potentiometer, that's a little pot, sometimes it's known as. And it's really just like it measures resistance. So the more that you turn the potentiometer, the more resistance it provides, or the less resistance. It's one way or the other. But essentially that's used to measure the angle, and this control circuit here will monitor that pot to see to what degree has this pot been turned, and therefore what can we work out from the servo horn itself. So it's kind of a feedback loop. The motor will turn this, and then the little control circuit will watch the potentiometer change until it reaches a certain value. So that's how they work internally. It's quite simplistic. They use a thing called pulse width modulation to control the angle which the servo's turning. So it's not quite what you'd expect. You'd expect that you'd plug the servo in and you could say from the Arduino on 90 degrees and the servo itself would figure this out, but that's not how they're created. They're quite simplistic inside. So every 20 milliseconds or every 50 times a second, there is a period of time that there is a pulse, and that pulse is called the duty cycle. And depending on what the duty cycle is, so you can see there we've got a very small one, 20 milliseconds, or we've got 2.2 milliseconds, 1.5 or 1 millisecond for the different duty cycles. They correspond to the different angles that the servo can rotate through. So so that's how they actually work. They receive this pulse width through the cable, through the orange cable, and the little control circuit can interpret that and go, alright, I understand what to do now, I can therefore turn the servo horn to whichever degree we've specified, but we do that through these duty cycles. So a little bit abstract there. And then there's another two different types, is analog versus digital. So the very cheap sort of transparent blue coloured SG90 servos tend to be analog. So they have a much smoother sort of waveform to them. Whereas the digital ones, they have a lot more, there's a lot more data being sent, if you like, but what that means is that it can hold the opposing force that it provides. It can resist these opposing forces greater than if it was just an analog servo. So one of the benefits there is that they're sort of a lot stronger, and it tends to be that the metal ones are also digital. So Tower Pro and Hero King, they're a couple of the common makes of servo. So you might see Tower Pro quite a lot on some of the sides of servos that you've seen online, and they're some of the most popular. But by far the SG90 is the world's most popular servo. So how do we connect this up to the Arduino? So on the right hand side of our Arduino, if we're looking at it sort of this top down orientation, we can see there's a number of digital pins that have got this little squiggle on, and what that squiggle means is that these can be set to be pulse width modulation pins. So we've got 7 different pins that we can go at there. So as long as we're using one of them, we can control straight out the Arduino 7 different servos. However, we can increase that number significantly by using a separate module, which is the PCA9685 board. So these are very popular. You can find these all over the internet. I know Adafruit provide quite a few of them. They've also got some nice software libraries to use with the Arduino and also with Python. And you can see there there's this power module at the top there, because a lot of these servos, they simply cannot be powered by the 5 volts that's coming through the Arduino. That's really just for signals. It's not really for sort of strength. So that really you provide some power into the side of the board using the ground and voltage here, but that's just to control this chip. The actual raw power that's driving the force of the servos is coming through this input. So here are all the 1 to 16 or 0 to 15 are the different places where you can put the servos in. I'll just grab one and I'll show you on the screen here. So I've got one of these boards here. I'll go full screen so we can see a bit better. So here's one of the boards. So you can see it's very similar to the diagram we had a second ago, and the sort of colour is yellow, red and black or brown, and they correspond. If I just hold up this servo I've got here, I've got a slightly larger servo. It's an MG995. So you'll see on there's 3 different colours, and the red one, which is the live one, is in the middle, and that means if you accidentally put this in the wrong orientation, the live is always going to be in the middle row, so you're not going to short out anything that you plug these into. So that's quite a clever design there. So if I plug this into a pin 0 on this little board here, that's what it looks like. So you can see you can have up to 16 of these things plugged in. So put that down there. So I've got a few of these we can have a look in a moment on our SMARS cam. A bit of a mess there, but we've got one just over here, and we've got a whole number of different servos here. We've got a very large one here. That's an 80588, and that's High Tech. They're another company that makes servos. Got a number of the similar type ones, and then there's some of the smaller ones down here. and there's the one that we took a picture before, the 20 kilogram one, and then there's an Arduino just here, just the back of the screen. Okay, so let's get back to the to here. Okay, so these use the I2C protocol that we've seen before. We used that when we were looking previously at the previous projects. We're looking at communication protocols and so on. And the top here of the board, there is a number of different areas that we can short these together. So you basically just solder across a blob of solder on these, and you can specify a new address. So you can chain these together on this side here. You've kind of got the same as is on the input, and you can basically chain these together and have a whole number of them, as many as there are different addresses available there. So that means from basically 2 pins, a clock and a data pin, we can have a lot of these. So a couple of pictures there, that's the size of them compared to our normal SMARS. There's a little 9-gram SG90 Servo, and there's our friend in the middle there. So let's go back to that. So on the back of the SMARS quad, you can see there's a little holder and a cover for the PCA9685 board, and it uses 8 of the servos, and you can see that there's 2 there. There's one here and one here. So one does the foot, one does the leg, and there's 4 legs in total. So we've got a bit of capacity there. We could increase the number of articulations if we wanted to on there, but that's how the SMARS quad is arranged. And some other robots as well that use servos, so you might have seen Auto DIY. Hi Camilio, hope things are going well for you. And you can see there he's got one in the top and one for his foot there. So there's one for the leg, one for the foot. And we've got OpenCat as well there. So I've got OpenCat next to me here. Just go full screen for a second to show you that. So this is OpenCat. So he's got a whole host of, again, 2 per each leg. He's got one for his tail, and there's one for his neck and one for his head. So there's got a whole host of them. And again, there's the board there, the PCA9685 board. So and we've got the 2 here I can show you. So that's the Auto DIY there, and we've also got our SMARS quad. So I've got 2 of these. I've got a white one and a grey one, and that one's currently powered by a Raspberry Pi Zero, and we can see there that's where the board is at the back. So that's what we have in the way of bits and bobs. Let me just get back to the presentation. And so this is what I've got set up on the board on the SMARS cam. This is more of a top-down view, just so you can see what's going on. I've added quite a few extra servos as well, just to make it a bit more interesting. I've got this DC power supply on my desk as well, just to my right, and this is what I use to sort of power these boards. So this input here is coming directly from the power supply, and it also means I can control it. I can give it 5 volts, and give it 12 volts. I can do up to 30 volts. And I can also change the ampage as well. I can throttle that back if I need to. And you can see on here as well, we've got various different pins plugged in. So I'm going to show you these one thing at a time, and we can understand what's going on. But essentially, we've got one servo plugged in. So we've got the red and the brown wire from the singular servo, and we've got the orange wire, and that's going to pin 9 on the Arduino. So the red is going to the 5 volts, the brown is going to a ground. And we've also got this PCA board, and these pins here, you can see there's a black and a white. The black and the white going to the 3 volts and the ground, and then there's like a grey and a sort of purpley coloured one, so sort of rose coloured one, and they're going to the clock and data. You can just see there, and the clock and the data for the I2C is just those 2 pins there. Okay, so let's crack on. So what I'll do, I'll just go to our split screen for a second. I've got my Raspberry Pi ready to go here. So let's go full screen in our Raspberry Pi. Hi Samo, how's things going? It's looking on the live chat. Great stuff. Okay, so let's go to our first program. So this one that's called sweep. So let's go full screen. So what I've done on here, there is a standard servo library which is provided as part of the Arduino IDE. So there's nothing extra that you need to add in there. This should be provided with the Arduino IDE when you install it. And what we're doing here is we've said, so we're including the servo library. Sorry, I was just pressing the wrong keyboard there. So yep, you can see on there we're using the servo library. We've created a servo and we're calling it My Servo. We're saying the position, this is going to store the angle of the servo, so it's currently set to 0. And then in the setup we're going to say myservo.attach, and 9 is the pin 9. So over on our Arduino, that's where we can see pin 9 is just over there. So back to our picture there, might be a bit easy to see. This is pin 9 over here. Okay, let's go back to our split screen and then back to Raspberry Pi full screen. Okay, and then further down in the main loop, what we're going to do is we're going to loop through position 0 to 180, and we're just going to step through one at a time. I'm going to delay for 15 milliseconds. I'm going to just write the position to my servo. So quite simple code, and then after it's done that, it's going to do the opposite way around, so it'll kind of sweep backwards and forwards. So let's go over to there. What I'm going to do is upload the code, and it'll spring into life right away. So let me just grab hold of that little servo, and let me show you that on the screen there. So you can see there it's just going through. There we go. So it's just going to keep doing that same pattern. So that's as simple as it is to create a servo routine. There's not very much to it. So what we'll do now, and that's great if you've just got 1 or 2 servos, or up to 7, because we've only got 7 PWM pins that we can address. But if we use the PCA9685 board, we can have 16 or more. So let's have a look what that looks like. So there's another piece of code here which I've prepared. So what I've done on here, I've gone into the managed libraries, and if you search for Adafruit Servo, there is an Adafruit Servo library that we can download. So let's just wait for that to appear, wait for that to update. And so if we just type in here Adafruit Servo on the right keyboard, and then wait for it to search through that. You can see there Adafruit PWM Servo driver library, and I got version 2.4 installed. So that's the first thing we need to do. I'm just going to go full screen now on the Raspberry Pi to make it a bit easier to see what's going on. And this is the code which is an example. So if we go, now that we've got that library installed, if we go to the examples and scroll down until we find the Adafruit PWM Servo driver library, there is one that's called Servo, and that's the sketch that I've got in front of me now. So if we look through this, we've got 2 includes, wire.h, that's our I2C, our badly named I2C library. Should have really called it I2C. And then the Adafruit PWM Servo driver library. We then create a Adafruit PWM Servo driver called PWM, and we initiate it. And there's a couple of defines here. What these defines do, you might have seen these previously. So unlike an include, or unlike a constant or a variable, this is just telling the compiler that we've got an option, and we can actually say if there is a definition of servo min, we can set we can do something. We can include an entire block of code. So it's a way of making a library or some code interchangeable. So you might use this if you had a production system and you had a development system, and you could basically just say define, debug, something like that, and it would only run that code if that flag was set. So it's really just for the compiler. These things don't end up in the code if they're not used. So a couple of things we've got there, servo min and servo max. So this is the pulse length, which is out of a maximum 4096. We have this US min and US max, and that's the minimum and maximum number of microseconds. And then we've got the servo frequency. So these things are to do with the duty cycle that we saw earlier. So if I just jump back to our keynote there. So it's to do with these different lengths. So where we've got, 1 millisecond, 1.5 or 2, and our entire period of time is 50 Hertz, we can actually specify, if we wanted to, different values for that. And that's what's happening here, the servo frequency. But they've set it to 50, which is good. And that means it's as per our diagram. We've then got the number of servos that we're going to, it's just a count to this. So that uint 8 is just a way of saying it's an unsigned integer. And it's basically just a smaller version of int. So we've got void setup. So we're going to begin by setting the baud rate. We've seen that before in our communications videos. I'll put a link up into the cards up here. Make a mental note that that's at 25 past 7. And we're going to print out 8-channel servo test, and then PWM, which is what we defined up here, which is our driver library, .begin. And then we're going to set the oscillator frequency and the PWM frequency. So don't worry too much about the oscillation frequency. It does mention in the blurb there what this is all to do with. And it's to do with if you're using this with different chips. And there's a function here that's called set servo pulse. So we specify a pulse, it does some calculations of that, and then it will set the PWM on that particular pin on a specific channel. So there are 16 channels, they correspond to the 16 different servos that we have. And then the main loop will go through, so it says whatever servo num is, so that's going to start out as 0, and then 4, and what it's going to do is it's going to loop through the minimum until the maximum, so it's basically going to create a sweep, and it's going to set the pulse width modulation for that particular servo for that particular length, which we defined above. So it's going to do that, it's going to wait for half a second, it's going to do it again, so it's going to go from it's going to go from small to large, and then from large to small, and then it's going to what else is it going to do? It's going to do the same kind of thing again, but with using the time difference instead. So let's upload this and see what happens. I'm just going to switch over to the SMARS cam to see, because all of a sudden these are going to sort of spring to life. There we go. So you can see it did it very fast. That one's moving very slowly now. There's the next one moving. So it did kind of a fast move, and now it's doing a slow sweep. There's the very large one at the back. Oops, the large one at the back there. That's a very powerful, strong one. We've got this one here moving. Got this one here moving. That's the 20. Much quieter if you notice that one. That was quite an expensive one. Got that one back there. My chihuahuas really don't like these moving. It's got to be said. Good girl. Okay, so they're going to carry on moving forever. I'm just going to stop these from doing this though, because my dog will not stop barking until I do. So let me go to full screen, and let's go back to the Raspberry Pi screen. And what I'll do, I've got the blink sketch. I always have this one handy in case something goes wrong. What we can do there is just flash that with the blinking program. There's my little chihuahua there, just going upstairs. She's not very happy with the servo noises that are going on. Okay, so let's go back to full screen. So you can see there, quite straightforward to get these things working. And what I thought I'd do as a sort of to show you these being used is, and it is a different language that I'll be using here. So I'm going to switch back to this view here, and what I've got open now, so this is on GitHub. This is the SMARS library that I created, which is a Python library, and I use it in quite a few different things, created about 2 years ago, and this relies on I2C and also a Python library called SMBus, and it's designed to run really on a Raspberry Pi Zero, and it uses the PCA9685 as well, so it's an Adafruit library. It needs to be installed on there, so you can see it looks very simple, similar kind of code there. If I just zoom in, so we're importing a time library. This helps us do time-based calculations. There's a module called logging that helps us log things out to file or to lots of different options actually for logging. You can log errors, you can log full debug statements, or you can log just basic information, and you can filter based on this logging level. So currently I've got that set to critical, so it'll report everything that happens, and that helps me when I'm creating the software and debugging it. And when I'm happy with that, I can set that back down to a much lower level or higher level of logging, so it doesn't report as much. I've then created something called channel. So a channel is a little class that I've created. And what classes are, if you're not familiar with those from a programming perspective, it's a way of sort of modularizing code and making it sort of a black box, so you don't have to worry about the inner workings of it. You just need to know what it does and what the functions are, and you can call them. So it's a way of sort of modeling more complicated things. So I've got a thing called a channel, so they represent each of the servo channels, and then in Python we have this try and exit. There's a distraction, man. Doggies. Sorry about that. So yes, we've got try and accept. So if there's an error, we can log out what the error is. And the most likely error that we're going to have is that the servo library driver isn't initiated, and it means it can't find the board. So if I'm running this, I can actually say, do not use the PCA driver, and set that to true. So it's just a shortcut really to say, I know that there's an error with the driver. We're just running this code in a sort of test function. And this means as well, when I'm uploading this to GitHub, it can do lots of tests on the code to make sure it's fine, and it won't have one of these boards installed on their servers. So this is just a little workaround. So that try, accept, and else is a nice sort of error trapping technique. Then similar to what we've seen in the code that we ran just a couple of seconds ago, which was the servo min and servo max, that's to do with the pulse width. And the sleep count is the amount of time that it waits between these PWM operations. So that 0.5 is what, 20 milliseconds? And then we can set the pulse width to 50 or 60. On this one I've got it set to 60. We could change that if we wanted to. And then we've got things like set the servo pulse. So it reads in a channel and it reads in the pulse, and then it will do some funky stuff on there to calculate what it needs to do, and then it will set the pulse width. And then what I've done for each of the limbs, I've created a different class. So there's a leg object. So the leg can have a minimum and maximum. It can have what I call the swing angle. So I grab this thing here. The way I've done this is that's the swing angle. So if it's set to swing, it's at a 45-degree angle. If it's set to body, that's set to that position there. And if it's set to stretch, that's about as far as it can reach. And each of them has their own swing and body position. So if I was set them all to 45 like that, they would all be therefore set to the swing position. And then the current angle is whatever the current angle is of the limb. And I put inverted there because if you think about how these things work, it's the same servo, but it's in a different orientation. So I want to sort of flip the orientation. So I've got some code there that can flip that round, and all I need to do is just say if it's inverted or not. And then what I've also done is some of these, because of the sort of logistics of where this thing can go, that can't go quite fully up to 180, and it might not be able to go down fully to 0 either. It's got sort of stuck at a 60-ish degree angle there. So this is a way of sort of locking in the minimum and maximum per limb, because each one's got its own characteristics. And similar with these ones that are on the actual leg, on the foot. That's the maximum height it can do. That's the minimum height it can do. So it's not quite a full range of 0 to 180. So we can set them for each of the legs and the feet. But what we've done here is, as I said, all 4 legs are the same, and then we need to configure the left, the right, the front and the back legs individually. So we initialize the class here. We've got some error checking to see if the driver's initiated. We can give the limb a name, such as front leg, back leg, front foot, back foot, that kind of thing. We can specify what channel it's on, so what servo channel it's on the little PCA9685 board. We can also say what the minimum and maximum angles are. We can say whether it's inverted or not. So if it's inverted, we do one set. If it's not, we do the other. So we can say set the body angle to be the leg max angle, set the stretchable to the leg minimum angle, and set the swing to be halfway between the 2 of those. And then the current is whatever the body angle. So we're just sort of saying set this to the body angle. So what all that means, we'll just quickly go through that. So what we're saying here, when we initialize it, is we're going to set the body angle to be whatever the maximum angle this leg can go to. We're going to say set the stretch one to be the minimum angle that this can go to, and set the swing angle to be somewhere halfway between the 2. And then we're saying whatever the current angle, we want it to be this body angle, which is there. We can set the defaults, and again that just says set it to halfway between the 2, which is our swing. And then set body, we'll set everything to be the minimum angle. Set stretch, which is like that, we'll set everything to the maximum angle. Set swing, we'll set everything to be the swing angle. And then up, we can say if we want the robot to be, that's down and that is up. So he sort of stood up or sat down, and there's a sort of middle way as well where everything's kind of halfway between the 2. And then show simply just prints out using the print function, and that'll print on Python to the terminal, a bit like our serial monitor. That will print things out to the screen. Hi Jonathan, how you doing? Long time no see. Set angle is a way of specifying exactly which angle we want this to be at. So we can, when we're actually getting this to walk, we want to be able to say precisely what angle we want this to be at. And we can do percentages, or we can do it as mapping the various different angles to different variables there. Now, one of the things I found when I was creating this walking pattern was it would very quickly move the leg. So there was no kind of graceful way that it would do this, and it would sort of rattle about and it would make it wobble quite a lot. I thought it'd be really nice if I could make this so that these things gently swung into place, and each one moved at the same time, rather than it moving one leg, and another leg. So what I thought about this quite a bit, and I thought it would be great if we could have it like a tick. So it's like a ticking clock. So you could say tick, and what that will do is it'll just move each limb one amount, and I've specified that to be 2. So it's 2 degrees at a time. So if we say tick, we can have a loop that says keep ticking, and it will tick until the maximum angle is reached on all of these 4 things. So when we do one, the loop runs around very quickly. And what actually looks like happening is that this is actually all the limbs are moving at the same time towards an angle. So what we do is we set the angle to be the kind of target that we want it to be. So if we say set the target to be, so if it's up like this in its stretch position and we want it to be in its body position like that, at this point we will say set body, and then we will tick, and this will very slowly move round until it reaches the body position like that over a period of time. And that period of time we can define in the loop that runs round and runs these ticks. So I've got untick and I've got tick. So untick goes backwards, and tick goes forwards. And it's quite a clever way, if I don't say more so myself, of making this look a lot more elegant rather than these things just zipping around and being quite inelegant. So I then model the SMARS robot itself. So as it says there, this is used to model the entire robot, its legs and its sensors as well, so things like the rangefinder. We could also include in here in future things like the battery level, the position that it's in to see if it's fallen over or if it's at an incline or a decline, or whether it's facing north or any other angle from the compass. We can say whether it's a wheeled robot or a quad robot. And I then set up two arrays, one for legs and one for feet. So the legs are these larger ones and the feet are these end ones. And then we name them. So remember before we created a name. So this one's left foot front. It's on channel 1. It's got a minimum of 50 and a maximum of 150. It's not inverted. Next one is left foot back. So as I'm looking at these, that's left foot front, left foot back, right foot front, right foot back. And you can see there I've worked out each of these and whether they're inverted or not. And we can just give it a name as well, and we can just print out the name is online. We can reset the leg position, so it just sets everything to the default, which we've set to be that sort of 45 degree. And we can do things like sit, stand, set swing, turn right, turn left, walk forward. And this is one of the most fun and frustrating things to work out, is the actual pattern of commands to make this go forward. So what I've done there, if you look at that, is we say we want the front. First of all, we set everything to be sat down. So self.sit. And what that does is it will sit the robot down, all the legs will go up like that. And that means that we can actually move these into position without it moving the robot. So that's why we sit it down first. So then we say, right, we want the left front leg to be in the body position. We want the left back leg to be in the body position. We want the right front leg to be in the swing position and the back leg to be the swing position. So it kind of looks like that. So that's the first cycle. Then for the number of steps that we're going to run through on this, we want to go through each of these. Remember, it's an array of legs. We want to go through that array of legs and we want to tick them. So they're all going to go through, and I think we also did a stand at the end of that as well. Yep, so that would make the legs stand up so that they sort of engage and pull the robot up. And then, while the current step is less than the number of steps, increment the steps and run through this loop. So it will then run through this series of steps to make the robot walk. And that is for walking forwards. There's a walk backwards, which is the opposite of that. Completely just reversed all the steps in it. Clap makes it get its little hands and do that. Number of times, however many times we've said to clap. And wiggle is it'll sort of do that and wiggle its bum a little bit. And we've got things like get telemetry as well. So this is a way of just getting the position of all the different limbs and sending it back to the calling function. And what I've done is I've created, if we go to SMARS fan and we look at the play and SMARSLab, you can see on there we've got things like the telemetry. We can read the angle of all the different limbs, we can see what commands we've given it, and we can press these controls here. I've not wired in the Bluetooth yet to this, but that's now very trivial to do. We could do that, excuse me, based on the last session we did on Bluetooth. So yes, we can issue these commands. We can stand up, sit down, we can clap, or we can wiggle. So we can build upon this, and I call this SMARSLab. It's just a lab for playing around with our SMARS robot. So that's pretty much it. There's some things I was doing there with colours, but we can ignore all that. Command history is all the different commands that we've been issuing to this, and we can just get the whole list or just the last 10 and we can clear them, and that's it. So that's SMARS library. and you can download that either from my GitHub account, or if you go to smarsfan.com, go back to smarsfan.com, just jump on that one there and then back. You can go to the play link, and SMARSLab and all the information about it is on there. So that's how all the steps to get it onto a Raspberry Pi Zero like this one. And this is the Zero with the it's got that sort of mirrored little thing there. You can see that shining. What that is the Wi-Fi chip. That's how you know you've got a Wi-Fi controllable. So if that's battery powered, it can be completely on its own, and we can also now add in the Bluetooth modules as well, so we can make that thing completely remote control. So that's how we can implement and use some of these servos for some fun. We've also got things like the Auto DIY. Definitely worth checking out if you're into small robots. This one's got sort of posable legs, and he can do all kinds of clever dances and things like that. So that's Camilio and his team have been working on that. And I think that's it for the servo piece. So what we'll be looking at on Friday is the line following module. So that's the thing that sits on the back or the front of the SMARS, and it can sense whether there is a black or white line in front of it and then follow that line along. So you can use black tape on the floor, sort of masking tape, something like that, to make it follow a line. So that's quite fun. So we'll be looking at that. That's a nice easy one for us to do on Friday. And you know, as I always say as well, you know, please like and subscribe to the channel. It really makes me understand who's watching, what videos they like, what they don't like. If you leave a comment on there as well, that also helps the engagement of the video and helps other people find it. And the other thing I was going to say, there's a couple of other channels you can find me on as well. So we've got Instagram. I post up quite a few videos and things to that. You can find me on YouTube, so it's /KevMcAleer28 for my channel on there, and on Facebook I'm Kev McAleer as well. So you can engage with me in any of those different ways if you want to chat about something. And yeah, please do check out the website as well, smarsfan.com. Put a lot of effort into that, and I'm continuing to increase these lessons. So I've got lessons 4, 5 and 6 currently sat waiting to be published, and I'll ping a note out on our Facebook group to let everybody know about that, and the other social channels as well. So yeah, please follow me on Instagram as well, at SMARSFan. And yeah, let me know what you think about this. So thanks for watching. We've had quite a few people watching today. I can see Samo and John, old friend from university there. And yeah, thanks everybody. See you very soon.